We're in the home stretch, grade nines. We have 2 topics left in electricity, then space, and we hit summer. So this is great. So what we need to know is that this week we're going to be doing 2 topics together. So electricity in your home is where we're starting, and electricity in your home, we have to get that from our power plants to our house. And so that is the main reason why we want to have AC power. AC power allows us to step up and step down the energy as it is traveled from where we produce our electricity to where we use it. So you don't have a coal burning power plant in your house, or at least I hope you don't. So you have to get that power transported from the coal burning power plant to your house, or from the wind farms, or from the hydro plant, or from the geothermal site. All of those things happen in specific locations. And so we need that energy to be able to transfer. To transfer it, you need to be having it able to go through those power lines. So once they get through the power lines, what happens? You're going to go from your power line. It's going to have a step down transformer, and it's going to go into your power meter. That power meter records the amount of electrical energy supplied to your house. After being metered, the electricity goes through the service entrance panel. The wires then are connected to the main circuit breaker, which is like a big giant switch that's like a safety device. So it is like a bimetallic strip. So you have 2 pieces of metal, and they're welded together, and you've probably talked about this in grade 7, but it's been a long time. And they actually heat up in different ways. So one will heat up faster and it bends the strip. So what happens is you have a circuit breaker. That means that when there's too much power going through, it'll actually break and open the circuit. So you will not have a power problem in your house. That's your main circuit breaker. Then it's going to go through each breaker, so more breakers, circuit breakers in your house, and then those go off into branch circuits. So if you are in your kit, like in my kitchen, if I use the kettle and the hot pot at the same time, plugged into different sides of my house, I can blow the circuit. So what happens is that circuit breaker heats up, breaks the circuit, those 2 things go off. I don't have the fridge go off. I don't have the stove go off. I still have power to all the other things in my kitchen, but those 2 are on the same branch circuit, which means that that circuit has shut off. So I need to go down, flip the circuit breaker, unplug one of them, and have patience so that I can make my dinner properly. So this is what all of that looks like. Is you have the transformer. Your transformers, you should go out and look on the power poles because they're quite cool once you know what to look for. This is your transformer out on your power pole, goes into the power meter at your house, and people come by and read your power meter. I'm going to show you how to do that in a minute. And then your electrical panels inside of your house, normally in a basement. And then each of these are what your circuit breaker looks like. And so mine don't actually go up and down, they go side to side, and I have to smash those over so that I can keep cooking. So in your house, you've got home wiring. If you're installed or changes need to be made, then you have this whole electrical code. So you always need to get like an electrician to come out and help you because they actually know how to do all of this stuff. I will be honest, I don't know a lot, but my cousin's an electrician, and he has told me so many different stories about all these different things that they can do and how they can make sure everything's safe. You don't want to overload circuits because that can cause a fire, but you also want to make sure your circuit has enough power and is not overloaded easily. It's great. So electrical devices. So in all of our devices, we have these electrical panels. And so they have conductors, which are wires. They have resistors and lamps and switches. So the switches, this one actually doesn't have a good picture of a switch. Oh, yeah, it does. This right here, this one that looks kind of like half of a circle, that is your transistor, and that's your switch. So there's quite a few of those normally. Here are your resistors. That's a capacitor. This is another thing, I can't remember what it's called, but it like does a whole bunch of coding. So those switches on and off, we have many, many, many of them in our electrical devices, and they actually use a code called binary code, and it's a series of on and off, and that's actually how you code things. So here, behind my picture here, there is this binary alphabet reference. So you could actually write out your name in binary code, which is kind of cool. It is not a requirement, but it's something you could do for fun. Now, as you've noticed, there's a little bit of math in this section. It's okay. You're going to be fine. Breathe through it. There's examples on how to do all of them. So, how do you measure power? So, power is energy over time. So, how do we figure that out? So, how much electrical energy we're converting into other forms of energy every single second. So, it's measured in, or the symbol in the formula is a P. It's measured in watts, and a watt is a joule per second. Now, joules you did in grade 8 with work and mechanical systems. So the formula is power is equal to energy divided by time, and that's your kind of your simplest formula. So here's an example of how to do it. I'm not going to read through all of this for you because there's a video that shows you that as well. So I'm going to keep this video short. So here's an example of also using it, but instead of using it just energy over time, because it could be any type of energy in that question, specifically saying electrical energy. So electrical energy actually means current times voltage. So power is current times voltage, and that's your other way of doing electricity power. So you can use both of those formulas. Again, here's this example. And then we go through a couple of examples, but I want you to go through those to make sure you know how to do them, okay? Now, paying for your electricity, how you do is you have to look at where it's sitting in the meter. So if you go and look on your house, you'll see all of these little meters. And what's really interesting is you start reading one this direction, like clockwise, then counterclockwise, clockwise, counterclockwise, clockwise. So here, you're going this direction. So this is past the 1, but not at the 2. So it counts as a 1. Whereas this one, if you read this direction, it's past the 7, but not quite at the 8. So it's a 7. And then on the next meter, you're going to go clockwise, and it's not quite at the 3. So you get a 2. And this one's a little tricky because it looks pretty close to the 7, but it's not quite at the 7 yet. So it's still considered a 6. And the reason for that is because this one is at a 9. So if you're ever not sure, look at the next one and it'll help you decide, because it's like which one you'd be the next closest to. So when you're doing this and calculating it for your house, you're going to calculate your last meter's number, this meter's number, subtract those two. That's how much energy you used within the month. And then you have to find out the cost per kilowatt hour. Now, the cost per kilowatt hour is actually an energy measurement, and we're going to be doing that throughout our apartment assignment this week. So I will be going through this in detail. But here's some examples. Please, please, please read through them. Please make sure you know what you're doing. And I will help you in class as well doing this. So then here's just like how you do this, by how much power, by how many hours, by how many days. It's how many kilowatt hours. It works out. It's not that difficult, and there's sample questions here, but I will also be doing them in class. So I like that I can just move myself all over the screen now. It's pretty exciting for me. Okay, so then we've got power ratings. So our power rating tells you how many joules of energy the device uses in every second of operation. And we use the Energy Guide and the Canadian Standards Association. So it tells you how much we use for that device every year. So once we know how much energy we're using, we need to know how efficient things are. So how much of that energy is actually useful energy? Now, this formula has a trick. It's so awesome. The trick is you need to always have the smaller number on top of the bigger number, because you can never have more than 100%. So if you ever get an answer with more than 100%, you mix these two up, you've done it wrong. So how does this happen? So incandescent light bulbs, for example, are only 5% efficient. And the reason for that is 95% of their energy is heat. They get really, really, really hot and they don't actually produce that much energy. Whereas halogen lamps are 15% energy. They get super hot, but it's only 85% of their energy. They give off way more light. And then you go to the fluorescents. The fluorescents are 20% efficient, which is a huge increase in efficiency from 5% to 80%. Now I realize that that's still not very good. And we are working always to get better and better and more efficient things. Right now, fluorescent, that's our max with light bulbs. So again, there's a few more questions, another video on how to do it. And then finally, just some reminders about electrical safety. Please make sure when you're at home, do not overload your circuits. So if you have like one of those plugins where it's 2 plugins and then you add another thing in so that you can now plug in 6 things, don't then plug in a power bar to that and add another 8 things. If you overload that, you can cause a fire. Never work on or clean appliances that are plugged in, because you don't want to have water and electricity. They don't work. Replace frayed or worn cords, and obviously water and appliances don't mix. Outdoor electrical safety, keep away from overhead wires. Never use undergrounded or frayed cords. Electricity and rain do not mix, and call before you dig. Hugely, hugely important. Okay, that wraps this one up. Have a great week, guys.